Hello there, this is Mrs. Sharp with some more half-life calculations. Today we're going to do type B. Type B problems, sorry about that. Type B problems ask how old is the sample or how long has the sample been sitting around giving off radiation, how long has it been decaying. This is how scientists use carbon dating to tell how old something is, like a dinosaur bone or a mummy wrap when they do an archaeological dig, something like that. So it's pretty cool. Ignore this, sorry. Here's an example, and we're just going to work our way through it. These are type B because you're looking for the words how old, how long, as opposed to type A that are how much or how many. So here we go. A 57.00 gram sample of radon-222. I'm going to stop right there. That is our original amount, so I'm going to call that N0. Contains only 7.125 grams of its original radioactive atoms. So in other words, it's decayed all the way down to 7.125. So that's how much that remains radioactive. We've been calling that N, and 57.00 grams is how much we started with. If radon-222's half-life is 3.8 days, okay, so I'm going to circle this. We're not going to need this until the very end. We're not going to need to know the length of the half-life until the very last step. And we want to know how old is the sample. So I want to show you guys the equation that we were using in type A problems. We're going to use the same equation, but we're essentially going to work it backwards. So the equation we used was this, N. So the amount that is still radioactive, that's what we were solving for in type A, is equal to the original amount that was radioactive multiplied by 1/2, because that's the definition, the definition of half-life, raised to the n power. That's a lowercase n. And remember that that small n is the number of half-lives that have passed. So I'm going to pause here for a second, and I'm going to write on the screen what each of these variables represents. And I want you to double check that this is in your notes somewhere. And if it's not, I want you to pause, and I want you to make sure that they are all labeled in your notes right this very second. Okay, so if you look at this, now each variable is defined, except for the blue 1/2 in parentheses. That's never going to change. That's there because of the definition of half-life, which is that half of your atoms are going to decay each consecutive half-life. So that we're never going to mess with. But the rest there are defined. So please make sure that those are in your notes somewhere. Another way to think about this, you guys, is by rearranging your N and N0. So like in this case, what is it that we will be solving for? We are being asked how old is the sample. So which variable are we looking for? The amount still radioactive, the amount originally radioactive, or the number of half-lives that have gone by? The only variable of those three that is a time unit, that is an amount of time, is this guy right here. So we're actually going to be solving for the exponent n. So I want to show you something here real quick. If I divide each side by N0, then the N0s would cancel on this side, and I would get N over N0 equals 1/2 to the N. And this N over N0 being written like this, we were talking about in type A problems as being that fractional percentage. So this is another way to write it that's helpful sometimes, since we know we're going to be solving for small n anyways. So that is the fractional amount left. So it's kind of like a percentage. If it told you that 12.5% was left, we know that the amount left was 12.5 out of 100, right? So if you're given a percent, you could stick it in that way. So it's just another way to think about it. Helps me wrap my brain around it a little bit more. So anyways, in this example, we know n and n0, and we're solving for n. So I'm going to clean this up, and we're going to plug in our numbers. Okay, so our N is equal to 7.125. So I'm going to put that one in 7.125 grams, and our N0 is 57.00 grams, and that is equal to 1/2 to the N power, and remember we're solving for that number of half-lives. So how do we get that N if it's an exponent? So here, don't be scared, but we're going to use a logarithm. First, I'm going to divide 7.125 by 57. Okay, in my calculator, that comes out to be 0.125. Okay, so 0.125 is equal to 1/2 raised to the N power. So to solve for something in the exponent like that, we need to use a log. So what we're going to do is bring that N out front. So it's N times, and because we did that, we're going to do log of 1/2. Okay, but because we did that to that side, to be fair, we have to do log of this side too. So we have log of 0.125 equals N times log of 1/2. And don't be scared of putting that in your calculator. So those of you who are using it on your, I know a lot of you are using your phones, and in your iPad calculator too. You're just going to punch in 0.125. Maybe it's still there from when you divided your 7.125 by 57. And then all you have to do is find the button that says log with like a little 10 that's below the G kind of. So that's called a subscript. So hit your log base 10. And when you do that, you're going to get negative 0.9. And I'm going to use 4 sig figs. Oh, shoot, I should have had 4 sig figs there. 0.903, and it's 0.8, so I'm going to keep it 1. Okay, and then I'm going to do the same thing over here, except for I'm going to keep my N equals N times, log of 1/2. So I'm going to put in 0.5 in my calculator, and then I'm going to hit that log, and you should get negative 0.3010. All right, and now I'm just solving for N. I'm going to divide each side by negative 0.3010. Negative 0.3010. And I get that N, if I divide those two, 0.9031 by 0.3010, they're both negative, so negatives cancel. I'm going to write it up here. I'm running out of room. N is equal to 3. Okay, and I have 4 sig figs in top and bottom, so 0, 0, 0 is what I get. And remember, that is the number of half-lives that have passed. So since each half-life is 3.8 days, I need to multiply those two by each other. It's not 1 half-life that's passed, it's 3. So I have to multiply 3.8 by 3 in order to get how many days old the sample is. So 3.8 times 3 is actually 11.4 days. And actually, I should have 2 sig figs. I have 3.000, that's 4, times 3.8, that's 2. So in order to follow sig fig rules, I could only have 2. So really, it would just be 11 days with 2 sig figs. Okay, so that was the last step of the whole thing, is where I brought in how long the actual half-life is. First, I found how many half-lives have passed. Then I multiplied it by the length of 1 half-life. This one is kind of misleading because it came out perfectly. We got exactly 3 half-lives, but it's not always going to come out that way. A lot of times you're going to get a really random number of half-lives, very decimally, so it won't come out so nice and perfectly. But if you look at this one, for example, if I took 57 and I divide it in half once, I get 28.5. That would be 1 half-life. If I divide it in half again, second half-life, only 14.25 grams of it would be radioactive. A third half-life, I'd be down to 7.125. So I could have figured out just by dividing it in half 3 times that 3 half-lives have passed. But what I'm saying is it's not always going to be nice and perfect like that. In this case, it was. So there we go. There is your example. Try your Type B practice problems, and we will go from there. Have a good day.